Hello, this is the third little lesson looking at an example of how to solve a trigonometric equation by adjusting the domain. And this is quite an interesting little one, this one. You'll notice, let's have a look at the domain first of all. The domain does not include any references to pi, nor does it have a degree sign, so it is definitely still in radians, but it's got numbers without the pi in it. And that almost always means that the problem has some sort of actual practical context, real world context. For example, I mean, this doesn't really make sense what I'm about to say, but let's go with it. Maybe this is the trajectory of a boat as it passes you from 2 seconds before it gets to you to 2 seconds after it gets to you. You know, and it just happens to the trajectory is modeled by this tan function. I don't know. So that's the kind of thing that you might have with it where it doesn't have pi. But you can still solve it. And this is how we do it. Do you remember what I said from last video, what we should do when we have a more complex expression like this inside our trig function? I wonder. Pause and think about it if you need to. What I said was the first thing you should do is factor out the coefficient of x. Now the coefficient in this case is pi. So I'm going to do that first of all, i.e. tan of pi outside of x plus 1. You can expand that later if you don't believe me, but these are equivalent, equals 1 for x between -2 and 2. I have not adjusted the domain yet because I haven't really changed the value of this inside here. All I've done is just taken out a common factor. Okay, so we're all good to go from that perspective, I hope. The rest of the process is kind of similar. Now this one here uses 1, so again, just to remind myself, I'm going to quickly draw a little diagram here. Now I know when 1s are involved, it's going to be that sort of pi on 4 kind of triangle. So we've got 1, 1 and root 2 as our three sides here, and I can see that because this is an isosceles triangle, both of these angles are pi on 4, and the tan of pi on 4 is equal to 1 on 1. So I'm just reminding myself, i.e. 1, we're going to be dealing with pi on 4 at some stage, but maybe that's a bit further down the track. Let's start as usual. Let theta equal pi outside of x plus 1. Then we have tan of theta equaling 1, and our new domain is, as usual, we do our substitution, and we're going to do it in our head like we did for the last example. So our boundaries are -2 and 2. So for -2, I go -2 plus 1 is -1. So I'm going to be having a lower boundary of -pi. Aha, we're back to pi land. And then for 2, I put 2 in here. I get 2 plus 1 is 3. And so my upper boundary for this domain is going to be 3 pi. So you can see our adjusted domain brings us back into pi territory, and that's comfortable territory for what we need to do. Okay, next step, can you remember? It's your old pal, theta hat. And we set theta hat, tan of theta hat equal to 1. We strip the sign off, whatever that is, and then we can state that theta hat is therefore equal to pi on 4 because of our exact value chart, or because we've drawn the triangle, or whatever else. So that's awesome. We've got that already. Now we draw our triangles and our unit circles, and we can see we're going from 0 to 3 pi. So I'll just need the 2 axes for that. So that'll be from 0 to pi to 2 pi. That's how I do it. And do another one from 2 pi to 3 pi, and then I can stop because I've hit my boundary. So that's not too bad. And again, I'm drawing these really big just so that we can sort of see it in the video. But if it were me, for real, I would be doing this, shorthand instead. Oh, I just realised we actually need a third one, don't we? And I should have done it first. Sorry, I meant to say I should be doing this a lot smaller than I am. It's not from 0, it's from -pi, I just remembered. Not worth starting the video again for it though. So we're going to go this way, and we're going from 0 to -pi. These other two are going in this direction. So I like drawing little arrows there so I can see what I'm doing. So I'm not going to consider this because we're stopping at 3 pi. I'm not going to consider this because I'm stopping at -pi. So these are our quadrants that are fair game. Now, we've got tan of theta equals 1, so we're looking at where tan is positive, and that's in the our first and third quadrant. So just looking at where the spare spaces are, it's going to be here and here and here, and here, and that's it. Again, I'm not really thinking about what the angles mean. I'm just looking at my white spaces and saying that's where tan theta could equal 1. Okay, now I'm going to put in my diagram, my unit lines. So that means I'm going to have one that's coming out of here, one that's coming out of here, one that's coming out of here, and one that's coming out of here. And in all cases, it is pi on 4 away from the x-axis. Now, I should have drawn this one first. This is the smallest. This is the next one. This is the third one here. Okay, so I can just go straight into going. Theta is equal to, and looking at the 4 quadrants, in that first set there, I've got minus pi plus pi on 4 here. So that's going to be minus 4 pi on 4 plus pi on 4 is negative 3 pi on 4. So there's my first solution. In the second one, I'm going to have pi on 4, and then I'm going to have pi plus pi on 4. So that gives me pi on 4, of course, 0 plus pi on 4. And then I'm going to have 4 pi on 4 plus pi on 4, which is 5 pi on 4. You can often see a pattern in the top here, which you can actually use if you want to. And then I'm going to have, in this quadrant here, I'm going to have, oh, sorry, wrong one. And then in this quadrant over here, I've got 2 pi plus pi on 4, which is going to be, what, 8 pi on 4 plus pi on 4 is 9 pi on 4. So again, once you start seeing the pattern, you can sort of pretty much do the cycle itself. And that is equal to pi outside of x plus 1, like so. Now, this is where it becomes really handy to have factorized out that pi first, because I'm going to divide both sides by pi, and that will nice and neatly just cancel out the pi's on the top. Okay, so I'm just going to go straight to that. So that will give me x plus, oops, wrong colour. X plus 1 is equal to negative 3/4, 1/4, 5/4, and 9/4, like so. So that's nice. And then I'm just going to subtract 1 from both sides to work out what x is. And when I subtract 1 from both sides, I'm just thinking in my head, I'm subtracting 4 on 4. So negative 3 minus 4 is negative 7/4. 1 minus 4 is negative 3/4. 5 minus 4 is 1/4. And 9 minus 4 is 5/4. And they are my 4 solutions. Quick check to see that these 4 numbers here do fit our original domain of it being between -2 and 2, and they do. I could also check on my graphics display calculator if I had one to double check, but if you can check on your graphics display calculator, you probably didn't have to do this in the first place anyway. Okay, that wraps up all of my different kinds of examples of adjusting the domain to solve a trigonometric equation. Your best job now is to go to your textbook or some other source and do as much practice as you can so that you can become fluent in this practice.